Welcome to Lecture 2 of our course. Today we're going to dive into the fundamental formulas that form the backbone of this fascinating branch of mathematics. Combinatorial analysis might sound complex at first, but I promise you that by the end of this lecture, you'll have a solid grasp of the core concepts and formulas that mathematicians and data scientists use every day. This lecture builds on our previous introduction and will be exploring the basic building blocks that allow us to count, arrange, and select objects in systematic ways, whether you're planning to work in computer science, statistics, or any field that involves data analysis. Understanding these formulas will be absolutely essential for your success. So let's begin our journey into the world of permutations, allocations, and combinations, starting with the fundamental question: how many different ways can we arrange or select items from a given set? Combinatorial analysis is the mathematical study of permutations and combinations of finite sets of objects. But what does that really mean in practice? Essentially, we're dealing with the art of counting without actually having to count everything one by one. Imagine you have a deck of cards, a group of people, or a set of digits, and you want to know how many different ways you can arrange them or select subsets from them. That's exactly what combinatorial analysis helps us figure out. It provides us with powerful mathematical tools and formulas that save us from having to list out every single possibility manually. The field has applications everywhere, from probability theory to cryptography, from logistics to game development. When you understand combinatorial analysis, you understand how to calculate possibilities, which is why it's such a crucial topic in higher mathematics. We'll be exploring three main concepts today: permutations, which deal with arrangements where order matters; allocations, which are ordered selections of a subset; and combinations, where order doesn't matter at all. Let's look at a concrete example to see how these ideas work in practice. The problem asks, how many three-place numbers can be made from the digits 1, 2, and 3 if each digit can be used only once? This is a classic permutation problem. To solve it, we use the formula p sub 3 equals 3 factorial, which means we multiply 3 times 2 times 1, giving us a total of 6 possible arrangements. Now let's actually list them out so you can see what we mean. We have 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and finally 3, 2, 1. Notice that all these numbers use exactly the same 3 digits, but they're arranged in different orders. Each arrangement is unique because the order of the digits changes the value of the number. This is the essence of permutations. Order matters. If we had used the digits 1, 2, and 3 to create three-place numbers, 1, 2, 3 is clearly different from 3, 2, 1. So when we're counting permutations, we're counting all possible ordered arrangements of a set of items, and as this example shows, the number grows quite quickly even with just 3 items. Now let's formally define permutations. Permutations are ordered sets consisting of the same n different elements and distinguishing only by the order of their disposition or location. In simpler terms, a permutation is an arrangement of all the elements of a set in a specific sequence. The key here is that we're using all the elements, and the only thing that changes from one permutation to another is the order. The number of all possible permutations of n distinct objects is denoted by p sub n and is calculated as n factorial. And what is n factorial? It's the product of all positive integers from n down to 1. For example, 5 factorial would be 5 times 4 times 3 times 2 times 1, which equals 120. This formula is incredibly powerful because it tells us that if we have a set of n items, there are exactly n factorial different ways to arrange them in order. As n grows, the number of permutations grows astronomically, which is why we need mathematical formulas rather than trying to list every possibility. Understanding permutations is your first step into the world of combinatorial counting. Next, we move on to allocations. Allocations are ordered sets composed of n different elements taken m at a time. These sets can differ either by the structure of their elements or by the order in which those elements appear. The key difference between allocations and permutations is that in allocations we're selecting a subset of the available elements, not using all of them, and importantly, the order of selection still matters. The number of all possible allocations is denoted by a sub n superscript m, and the formula is n times n minus 1 times n minus 2, continuing until we've selected m terms, which simplifies to n factorial divided by n minus m factorial. So if we had 10 items and we wanted to select 3 of them in a specific order, the number of allocations would be 10 times 9 times 8, which equals 720. Allocations are incredibly useful in situations where you're selecting a team in order of seniority, ranking candidates for positions, or creating sequences where the order of selection matters, but you don't need to use every single item available. Let's work through a practical example of allocations. The problem asks, how many signals is it possible to make from 6 flags of different colors, taking 2 at a time? This is a perfect allocation problem because we're choosing 2 items from a set of 6, and the order matters, since a signal with a red flag followed by a blue flag is different from a blue flag followed by a red flag. Using our allocation formula, we calculate a sub 6 superscript 2 equals 6 times 6 minus 2 plus 1, which is 6 times 5, giving us 30. Alternatively, using the factorial formula, we take 6 factorial divided by 6 minus 2 factorial, which is 720 divided by 24, also giving us 30. So there are 30 possible signals you can make with 6 flags taken 2 at a time. What's really interesting is that if you think about it, the number of allocations grows quickly. With 6 flags and taking 2 at a time, we have 30 possibilities, but if we were taking 3 at a time, we'd have 120 possibilities. This shows just how powerful combinatorial formulas are for calculating possibilities efficiently. Now we come to combinations, which are closely related to allocations, but have one crucial difference. Combinations are sets composed of n different elements taken m at a time, but unlike allocations, combinations are only distinguished by the elements they contain, not the order in which they appear. In other words, with combinations, order doesn't matter at all. If you're choosing a committee of 3 people from a group of 10, it doesn't matter whether you choose Alice first and Bob second or Bob first and Alice second. The committee is the same. The number of all possible combinations is denoted by C sub n superscript m and is calculated using the formula n factorial divided by m factorial times n minus m factorial. This formula has a built-in division by m factorial because we need to eliminate all the different orderings that were counted in allocations but shouldn't be counted separately in combinations. Combinations are used everywhere from lottery calculations to team selections, and understanding when to use combinations versus permutations is one of the most important skills in combinatorial analysis. Let's look at another example to solidify our understanding. The problem asks, how many ways are there to choose 2 details from a box containing 10 details? Since the order in which we choose the details doesn't matter, this is a combination problem. Using our formula, we calculate C sub 10 superscript 2 equals 10 factorial divided by 2 factorial times 10 minus 2 factorial. That gives us 10 factorial divided by 2 factorial times 8 factorial. When we simplify, we get 10 times 9 divided by 2 times 1, which equals 45. So there are 45 different ways to choose any 2 details from the box. Now here's an important relationship to understand. The numbers of allocations, permutations, and combinations are connected by the equality A sub n superscript m equals P sub m times C sub n superscript m. This means that the number of allocations equals the number of permutations of the chosen items times the number of combinations. If we know any 2 of these values, we can always find the third. This interconnected relationship is one of the beautiful symmetries of combinatorial mathematics. When solving problems in combinatorial analysis, we rely on 2 fundamental rules, the sum rule and the product rule. Let's start with the sum rule, which states that if an object A can be chosen by m ways and another object B can be chosen by n ways, then choosing either A or B can be done in m plus n ways, assuming the choices are mutually exclusive. To illustrate this, consider a box containing 300 details with 150 of the first kind, 120 of the second kind, and the rest of the third kind. If we want to know how many ways we can extract either a detail of the first or second kind, we simply add the number of ways to extract the first kind, which is 150, to the number of ways to extract the second kind, which is 120, giving us a total of 270 ways. The sum rule is incredibly straightforward, but it's used constantly in combinatorial problems. It applies whenever you're faced with an either-or situation where you need to choose one option from multiple distinct categories. The product rule complements the sum rule perfectly and is arguably even more widely used. The product rule states that if an object A can be chosen by m ways, and after every such choice, an object B can be chosen by n ways, then the pair of objects in that order can be chosen by m times n ways. Let's look at an example to see this in action. Suppose we have 30 students in a group, and we need to choose a leader, its deputy, and the head of the professional committee. The leader can be chosen from any of the 30 students, that's 30 ways. Once the leader is chosen, the deputy can be chosen from the remaining 29 students, that's 29 ways. And after both are chosen, the committee head can be chosen from the remaining 28 students, that's 28 ways. By applying the product rule, we multiply all these together. 30 times 29 times 28 equals 24,360 different ways to fill these three positions. This rule is essential when you have sequential decisions or when you're choosing multiple items in order, especially in allocation and permutation problems. Now we transition from combinatorics to probability theory by introducing operations over events. In probability, we work with events, and we need ways to combine them. We define three fundamental operations: sum, product, and negation. The sum of two events A and B is a third event, denoted A plus B, which represents the occurrence of at least one of these events. This is essentially the union of events in probability theory. The product of two events A and B is a third event, denoted AB, which represents the simultaneous occurrence of both events A and B. This is the intersection of events. An important special case occurs when A and B are incompatible events, meaning they cannot happen together. In that case, their product AB is an impossible event which has probability 0. Finally, the negation of an event A is the event not A, which represents the non-occurrence of A. The sum of an event and its negation always gives us a certain event, while their product always gives us an impossible event. These three operations form the foundation for all probability calculations.